So types of chemical bonds. Chemical bonds form because they lower the potential energy between the charged particles that compose atoms. So atoms have protons and neutrons in the nucleus, and then there's electrons outside the nucleus, and now you kind of have an idea of, yeah, that's a big can of worms talking about what those electrons are doing. But we have negative particles and positive particles. The electrons are going to repel each other, and the nuclei are going to repel each other, but the electrons from one atom can be attracted to the nucleus of the other atom. And so how do these attractions and repulsions work together? When does a bond form? When does a bond not form? Well, a bond will form if all of those interactions together result in a net reduction in energy. If this is going to be lower in energy, the bond will form. If it's going to be higher in energy, they're like, nah, not going to do it. Don't want to go up the hill. No balls rolling up hills. So one kind of a bond is an ionic bond. And this happens between metals and nonmetals. And so this is kind of repeating some of the stuff we learned about in chapter 3. We learned to name and write formulas for ionic compounds. And we learned that ionic compounds have a metal and nonmetals, right? Well, now we can understand why this is. Metals have low ionization energies. It's relatively easy for them to lose electrons. They form cations. Nonmetals have negative electron affinities. They will gain the electrons and form anions. And then the positive ions and the negative ions are attracted to each other. So when a metal loses an electron, it doesn't just like go off into space. It has to go to something. And so the metal transfers one or more electrons to a non-metal and says, okay, I don't want these anymore. Here, you take them. They're yours now. And then we have two ions. And then the ions are attracted to each other. Any questions about that?
Just kind of to clarify, like, because the metals that we're talking about are not the transition metals, because sometimes or the transition elements, because sometimes they gain and sometimes they lose, right?
No, the metals always form cations.
Okay.
Metals always
But
form
they
cations.
can do that at different.
They can form more than one cation.
Okay.
They might form +1, +2. Some of them, I think this manganese, can be +1 up to like +7. Yeah, really kind of weird. But they're always positive. This table here summarizes three kinds of bonds. Ionic bonds, we're just talking about that, between a metal and a non-metal, electrons get transferred. Next we'll talk about covalent bonds, where we have two nonmetals, and there we don't get a transfer of electrons because the nonmetals both want to gain electrons, and nobody's willing to give up electrons, so a transfer can't happen. So they share instead. And then we also have metallic bonding, which is between metal atoms. And so in a pure metal or in a metal alloy, that's what's holding the metal atoms together. And the characteristic of that bond is that the electrons are pooled. They're not really shared or transferred. They're just kind of, there's an electron pool. Oops. Covalent bonding. So the nonmetals are going to share some electrons. Those shared electrons interact with both nuclei, and so they have the effect of pulling the nuclei or holding the nuclei together. The most stable arrangement is one like this, where the shared electron or electrons are between the two nuclei, because that maximizes the attraction for that electron to each of the nuclei. If the shared electron is equidistant but off to the side, or if it's over here closer to one or the other, that's going to be a higher energy and it's going to be less stable. So those negative electrons that are being shared hold the positive nuclei together. And then in metallic bonding, this is between metal atoms. Metal atoms lose electrons easily to form cations, but they don't want to gain electrons. And so unlike the nonmetals, and women tend to be real good about sharing stuff, and guys are like maybe not so much into the sharing with each other. So what the metals do is they just kind of pool their electrons. And so the electron C model is the simplest model. All the atoms in the metal lattice, so you've got a bunch of different metal atoms that are all lined up in this solid, and they're going to pool their valence electrons. And so the valence electrons are just kind of free to roam about the entire piece of metal, kind of like a sea of electrons. I also think of this a little bit like a neighborhood. I have all these weird stories. I'm going to break them up pretty much every semester. They sometimes get variations. So if we think about a chunk of iron, I'm just going to draw 4 of them. How many valence electrons does iron have? Valence electrons. 2? What? Well, it's over in that 3D block. So it's got a bunch of 3D electrons. Those aren't valence electrons. The valence electrons are the 4s. 2 valence electrons. Okay. So each of these iron atoms has 2 valence electrons. It's going to send those electrons out. So I think of these atoms as being like houses in a neighborhood. And electrons are a lot like my son Andrew, a little bit squirrely and unpredictable, and like little boys. And so this household has 2 little boys, and they get sent outside to play. This is how things were when I was growing up, especially in the summer. Mom would send you out to play, say, come back when the streetlights go on. Yeah, and in Minnesota, that might be 10 o'clock. So yeah, don't want to see you, just go out and have fun. And we did. It's a different world, you can't really do that anymore. But so the electrons get sent out to play. So here's an electron, and here's an electron, and here's an electron. And so everybody's sending their electrons out to play. And so you've got this herd of electrons running around the neighborhood. But everybody has sent electrons out to play. And so if you hear screaming out there, you're like, well, it could be my kid, right? So you're not just going to ignore it because, well, my kids are sitting here watching television. They're all outside. So it kind of pulls the neighborhood together because everybody's kind of watching out for everybody else. So that's the electron C model. The pooled electrons are keeping the atoms together.
But it's not as strong of a bond as like a covalent.
It's a very different kind of bond than an ionic bond or a covalent bond. And we'll talk about this later, but I just kind of feel like it, so I'll talk about it right now. Metals conduct electricity, right? In order for something to conduct electricity, you have to have charged particles that are free to move. These electrons are delocalized over the whole piece of metal. They can move. So if this one moves over here, another one can come in and fill its spot, and so the electrons can move, so metals conduct electricity. The attraction that these electrons and the atoms have for each other is not directional at all. And so if you hit this chunk of metal with a hammer, and it will dent, it'll just kind of smush, right? Because the bond, this electron C, is flexible. And if you move something out of place, it's like, oh yeah, but you're still part of the group. When you have an ionic compound, you have the ionic bonds are going in multiple directions, but they're also very dependent on the distance between the 2 particles. And so if you hit an ionic compound with a hammer, it tends to shatter. A block of ice is somewhat like that, although it's not ionic. But maybe a mineral, a gemstone, and you hit it and you can actually get it to break in a nice straight plane, right? Because you're separating the ions and you'll get these nice planes, and you can make you could chisel it into certain shapes. You can't go against its natural crystal structure, but you can go with the crystal structure and do cool stuff. But that's kind of a preview of things to come.
So for atomic bonding, that's only when you have a chunk of the same metal, right? You can have a compound composed of two different metals.
That's an excellent question. So this is the case for any combination of metals.
Okay.
So when you have two metals together, it's not actually a compound. It's a mixture, and we call those alloys. So things like stainless steel are alloys, or gold that's used in jewelry. There's 24 karat, there's 18 karat. That's how much gold relative to how much of other metals are in there. And the other metals are added in there not to save money so we don't have to use as much gold. It's because the gold itself is too soft to be useful as a ring, and they'll get bent out of shape. So you add some other metals in there to change the properties of the metal.
That's why we can mix so many metals.
Yeah, so metals mix together really well. Now, you have to melt them to get them to do that. You can't just put a chunk of iron and a chunk of I don't know, manganese or something next to each other and say, okay, mix. They won't do that. But if you melt them, they will mix. And then you cool them down, and they will stay as a homogeneous mixture.
So when you have metals that are melted down into an alloy, they're pulling their electrons the same way, and that's why alloys
Yep.
can be conductive.
Yep. So they're going to do the same kind of bonding. And that's a whole nother field, is looking at material science, right? How can we change the properties of this metal? I need it to be very lightweight, but I also need it to be strong. I need it to do this, but not that. And so what different combinations can I put together to get those desired properties? Can be very interesting.